Our next speaker is Yusen.
Okay, can you hear me? Yeah, it works. Okay. So I will present some of our PIES work, inverted echo sound and pressure sensors around Sri Lanka, and it connects very, very closely to the glider presentation that you just heard. It's also about capturing the kind of gateway exchange around Sri Lanka between Bay of Bengal and the Arabian Sea. And in some sense, you can think about it as adding a high-frequency component to these glider sections that we just saw, which have a temporal resolution of a few weeks. And here we, in principle, get hourly data, but since it's geostrophic, it's a matter of timescales of a few days that get resolved. So the basic idea and what we have in the water at the moment are pairs of PIES, one on the east coast here and one on the south coast. And by design, they lie exactly on the glider sections. So that was a very nice cooperation we have with the UW team. So the PIES transit along the glider sections. And as I said, we are trying to capture the mass transport through these two sections with high temporal resolution, observing the intra-seasonal, but of course also longer time scales. And what we get directly are the volume or mass transports, and by combining it with other data sets like the gliders or satellite and numerical models, we hope to obtain exchange of fresh water around Sri Lanka. So a few words about the methodology. So the instruments we use are these inverted echo sounders. The inverted echo sounder with pressure sensor is the bigger white sphere here. It has an acoustic transducer that sends a travel time signal to the surface and measures the travel time, which is actually more a measure of the temperature along the path than the sea surface height elevation. And it has a high precision pressure sensor, so we get bottom pressure. And the black thing is an acoustic modem, which we use to retrieve the data acoustically when we go there with a ship. We can also do it with gliders, if we had gliders there that are equipped with a modem and so on. This is the Samudrika from NARA that we use for deployment, recovery, and the acoustic data transfers. And just like the glider work, this is very closely coordinated between our project and the people at NARA who are collaborating and helping us in many different ways. So one slide about the kind of calculations behind it. You may know that the traditional method to analyze PIES data, acoustic travel time data, is called Gravest empirical modes. That's essentially just a simple one-dimensional lookup table between travel time and temperature and salinity profiles based on historical data in the region. That doesn't work here because it's a much more complicated hydrographic structure. If you try to make a lookup table, one-dimensional lookup table, you get huge uncertainties and errors, which is not useful for constructing dynamic height. So we figured that instead of trying to resolve kind of depth-resolved density or dynamic height profiles, let's just try to estimate directly from the travel time the quantities we want, which is really a double integral of the specific volume anomaly, because the geostrophic current at a single depth is a volume already of the geopotential anomaly, or integral of the specific volume anomaly. And the transport over a layer is again a vertical integral. So the quantity we want, the transport over a layer, say from 0 to 200 meters depth, is a double integral, and therefore it's a much less sensitive quantity. It's much easier to estimate from integral measurements like bottom pressure or acoustic travel time or even altimetry. So therefore we define this quantity in terms of the double integrals of specific volume anomaly, and these integrals we call geopotential integral. So this is essentially the two parts of this integral separated. And then if we difference those, that's the transport we want. So the trick now is to construct essentially a lookup table for this geopotential integral, or the double integral of the specific volume anomaly, between so a lookup table to estimate this from what the PIES measures, the travel time. And since we found this is a more complicated region with more vertical layers, we decided to also throw in satellite altimetry data. So we're making a two-dimensional lookup table using as inputs travel time and altimeter SSH, in order to recover this geopotential integral. And that turns out to work quite well. So this is an example of the correlation that you get if you simulate this geopotential integral that we want, this on this axis, with the one predicted from historical data. So that's the correlation with which we can calculate the two endpoints which we difference to get the transport. So this is the input, the lookup table essentially, or the correlation of the lookup table. Then we looked at historical profiles to decide over which layer we want to form this double vertical integral, and we decided upper 200 meters is a good estimate for the surface boundary currents that we want. And then we had to decide on the length of the section, and we used analyses of 2 decades of satellite SSH. This is a Hofmüller plot of the SSH anomaly on the eastern section. Sri Lanka is here, and we define this as the width of the boundary current that we want to observe. So we deployed 1 pies here and 1 pies at 83.5. We did the same thing on the south, satellite altimeter SSH annual cycle, and we defined this as the width of the boundary current and deployed 1 pies here and 1 pies here. And that's how we define the length of these sections. And by the way, you see here the semi-annual signal on the eastern section in SSH and the annual signal on the southern section, and we find the same in our observations. So I mentioned this already, and from the previous talk you saw it. These are exactly overlapping with the glider sections, and we have some ideas of how we can put these together going forward. In terms of the logistics, we use this ship. We usually try to go once a year to download the data. This is the simple over-the-side acoustic modem with an acoustic deck unit and a computer logging the data. Last time we could get there was on in November 17, since much of 2018 the ship had problems. So right now we only have 3 years of data in hand from the East Coast and 2 years on the South Coast, even though there is a year more of data waiting for us to be recovered. And the pies on the East Coast section that need to be recovered urgently. They have been in the water for over 4 years, and the batteries are going to run out very soon. So this is now the analysis of the transport time series on the eastern section. The two so the sheared part, which we derive from this two-dimensional lookup table, is the blue curve derived from altimeter and acoustic travel time. And then we reference that to the bottom pressure measurement, because all the dynamic height transport estimates are referenced to a reference layer, and we chose the bottom where the pi's pressure signal is measured. And that part contributes this barotropic curve, the red one. And if you add those up, the black one is the total transport to the section. And these are the years of data we have in hand. And you see the semi-annual signal, which we saw in the altimeter. This is kind of flipped around to line this up. So this is the coast of Sri Lanka. This is the width of the boundary current. And these are the seasons here from January to December. It's northward here, southward here, northward here, southward here. And you see this same behavior in the continuous measurements. But the big message here, I think, is there are very large interannual changes. Every year looks very different. And there are lots of high-frequency changes, too, which we haven't been able to capture with other methods so far. So this is the same result for the southern section, again for the 0 to 200 meter layer. The sheared part referenced to the bottom in blue, the barotropic component from the pressure signal in red. Black is the total curve. And here we have overlaid the time series that we have until now with Julie McLean's model output from different years. These are all the gray lines, and the battery is dying on me here. So you see it's in the envelope of the annual variability. Here we tried the first comparison with the UW gliders. These are the same transport, 0 to 200 meter layer over the same section, estimated from the gliders. Those are the red symbols here for the east section and for the southern section. And you see there's generally good agreement between those when there are gliders available, and we are working more on this comparison. We started some very simple preliminary steps into looking into freshwater and salt transports. So this is an attempt to combine our pies volume transports, that's the black line, with SMAP, say surface salinity, that's the blue line on the eastern section and the southern section. And we were hoping that there's a correlation which gives us a salt transport. So on the eastern section, there's not a very good correlation. On the southern section, there is quite a strong correlation. And if you try to calculate the salt transport from that, you get 1.2 times 10 to the 6 kilogram per second, which is approximately 25% of the salt budget for the Bay of Bengal. But there is something funny, it seems here on the eastern section. And if we look a bit more closely, again, these are now the SMAP salinity Hofmiller diagrams. On the southern section, there's a nice seasonal cycle, as one would expect it, this fresh water coming out of the Bay of Bengal in winter. But on the eastern section, it looks more messy and not so clear. So we are wondering whether something unusual might be happening in these years, at least on the eastern section. So we looked at longer time series in altimetry and the Indian Ocean Dipole Mode Index. And this is now going upward in time. And you see there's, in the recent years, very large, unusually large swings in the dipole mode index. And that goes together with the more red colors in the altimetry map. And in the bottom picture, you can see that in the last years, it was the largest dipole index in the last 25 years. So maybe something unusual is happening in the boundary current east of Sri Lanka during this period. We also discovered an undercurrent on the east coast of Sri Lanka while doing all these analyses. During 2 seasons here, they are reversing surface and opposing intermediate currents. So here in the spring season, it's positive at the surface and negative below that. And in the summer season, it's the other way around. There's negative flow at the surface and positive flow below. So this is the seasonal reversing undercurrent we found using different data, CTD and Argo. You can see it in the glider data and in HICOM and POP model data as well. And we can even extract that layer in the PIES measurements using the same method, this geopotential integral. Instead of doing the lookup table for 0 to 200 meters, you can try to make a lookup table for 200 to 600 meters, and then you get a curve that gives you the time series, the transport of this intermediate layer. And again, we try to extract the similar measurements from the gliders. There's a lot more scatter or not as much signal compared to the noise, but at least they seem to be consistent, and just wanted to show that that seems to be possible too. So that's the last slide, the current status. So we think we have been able to show that this new method works and gives high frequency time series of the volume transport on both sections. We are now working on combining this with other data like the gliders collaborating with the UW team, with altimetry, with SMAP and models. We urgently need to recover both the PIES and more data since the last data we have since 2017. We are trying to recover the eastern PIES with an ARA ship in a few weeks. We have some hope to get access to the ship. But we will also be using the Sally Ride transit leg in the summer from Colombo to Chennai. That's 4 or 5 days. And we will either recover or redeploy the eastern PIES and do data download from the southern PIES. Thank you.